In this video, we are looking at another integral operator, and the one we will look at is the surface integral. This is our overview slide, which will spend about 5 minutes just taking a look at what we will cover, and then after, we will go through each topic in more detail and with more examples. The first topic we will cover is the surface integral itself. Its symbol is this integral over the surface S d sigma. And here we have a picture of a surface, or my attempt at a picture of the surface, where we have d sigma is a vector that represents the area of the surface, and the vector has a magnitude equal to the differential area of S and a direction perpendicular to the surface. Because the surface has two sides, we choose to define the positive orientation of n as pointing outward. We will discuss orientation of a surface that is not closed later in this video. Because we are talking about surface integral, it's important we understand how to parameterize a surface. And our view of a surface is going to be of this function phi, which maps something in R2 into R3, into three-dimensional space. So it's helpful to think of this as we start off with a portion of the plane, and here I called it the UV plane. So some domain in R2 that then gets mapped into three-dimensional space. And this mapping is what gives us our surface. It takes a domain, maps it to a surface. The three surfaces we will parameterize will be a sphere, a cylinder, as well as a cube. Once we know how to parameterize a surface, we can use this surface integral operator on a vector field using the dot product. So we're going to do surface integrals of a vector field, and the symbol here that we have is the integral of this integral over the surface d sigma dotted with v, our vector field. Actually, I should put a line on top of my v since it's a vector. And the steps to doing this integral here is to first parameterize our surface and determine its domain, D. So here we're going to parameterize, find this mapping, and so we have our domain D, which gives us our limits of integration, and then our mapping, which helps us determine our surface. The second step is to write our vector V in terms of our parameterization. So in this case, V, since it's a vector field, the vector field is defined all over, throughout our three-dimensional space. However, we're only interested in the vector field that is on our surface. For that reason, we do V composed of our surface. The next step is to calculate the normal, and the way we do that is we cross the tangent vector in the u direction with the tangent vector in the v direction. And then because we have u cross v, the tangent vector in the u cross the tangent vector in the v, we get a vector normal to both of these, which will be normal to our surface. Then we plug it into our formula. So now that we have all these different components, we evaluate the surface integral d sigma dotted with v by taking the integral, the limits. It's a double integral here because it's over the domain, our phi of uv dotted with tu cross tv. So this is our phi, our surface composed, our vector composed with our surface, and then our vector normal to the surface. And we will work out this example here where we compute the surface integral of the radial vector field r of x, y, z over the surface of a unit sphere. And the last note that I have, it's more of a note than a topic, is a physical interpretation for the surface integral operator, and that is a flux. This surface integral will give us the rate of flow across the surface. That concludes the overview, so we can start again back up at the surface integral operator. We notate the operator for surface integral as the integral of s d theta, where d theta is a vector that represents the differential area. So if we're integrating over a surface, the small piece of area that we're integrating is our d theta, and the vector has a magnitude equal to the differential area in S and a direction perpendicular to the surface. If the unit normal is n, it's perpendicular, the differential area vector becomes, because the differential area vector is also perpendicular to the surface, then d theta is equal to n. Here we have the direction now goes towards the normal, and then we have d theta. Because a surface has two sides, we choose to define the positive orientation of a closed surface as pointing in the outer direction. So if we have a sphere or maybe a box, the positive orientation is pointing outwards away from the center of our closed surface. If the surface is not closed, i.e. it does not include a volume, the positive direction of the normal is defined by the closed path that defines the boundary of the surface. And we use the right-hand rule. So, for example, here we have a surface that looks a lot like a circle, looks kind of like a lot like a golfing putting green, but anyway, it looks like a circle, and we're looking at the boundary now. And the way we determine the orientation, the positive direction, is we imagine walking around the boundary in such a way that our left hand continually points towards the center. So you can see this golfer, his left hand and his golf club is always pointing towards the center of the circle. So that kind of gives us a direction. So once you have a direction, think of curving your fingers around in this direction here. And as you curve your fingers, your thumb will point in the positive direction of n. So what we've discussed is true of this general surface operator, integral operator, and we'll see what happens when we use this operator on a vector field with the dot product. But first, before we go to this part here, we need to talk about parameterized surfaces. When we talk about parameterized surfaces, it's useful to think of a parameterized surface as a mapping, something that takes a domain in R2 and maps it into three-dimensional space R3. So here's kind of an illustration. The idea is we have our three-dimensional space here with the UV plane instead of XY, because we're going to map to the XY. So we have something in the UV plane. A portion of this plane is going to be our domain, which I have shaded in yellow here and labeled with D for domain. And the idea is we take this portion of the plane, we apply our mapping phi onto it, and then it becomes a three-dimensional, something in three-dimensional space. It becomes a surface. So the surface is equal to phi applied to some domain in two-dimensional space. So the notation here is phi goes from R2 to R3. So phi of UV gets mapped to an x-coordinate, a y-coordinate, and z-coordinate in three-dimensional space, where x is dependent on UV, y is dependent on UV, and z is dependent on UV. So here our parameterized surface phi is the map to get the surface to twist or bend a region in the plane to yield a surface in R3. At a particular value for u and v, we can evaluate a tangent vector in the u direction, and we do that by taking the partial derivative with each coordinate with respect to u. So in other words, tu will equal to partial derivative of x of I du evaluated at u naught v naught times our direction vector, the ith direction vector. So if x1 is equal to the x direction, x2 is equal to the y direction, and x3 is equal to z direction, this becomes dx du evaluated at u naught v naught times the basis vector in the x direction, plus dy du evaluated at u naught v naught times the basis vector in the y direction, plus dz du times the evaluated at u naught v naught times the basis vector in the z direction. Similarly, you can get a tangent vector for v. And now if you have a tangent vector in the u and v direction, to get the normal to some point on this surface that u naught and v naught map to, you will cross tu cross tv, tu cross tv. So that will give us our vector normal. I have made note of my TU and my TB as well as my normal vector equal to TU cross TV over here. We will come back to this shortly and we will be using it. But before we use this, let's do some parameterization of particular surfaces. The first one is the surface of a unit sphere. We start by noting if we wanted to parameterize an entire sphere, not just the surface, but an entire sphere, including the interior, we will use spherical coordinates. So we'll have rho cosine theta sine phi, rho sine theta sine phi, and cosine phi. And then theta will go between 0 and 2 pi, phi would go between 0 and pi, and rho goes between 0 and r. And again, these are just spherical coordinates and should look familiar to you. From here, if we want to parameterize just the surface, our angles range have the same range. However, what we will do is hold our radius constant. So if we want the unit sphere, our radius, our rho, will be held at 1. So now we have our parameterization. This is phi of theta phi is equal to 1 cosine theta sine phi, 1 sine theta sine phi, and 1 cosine phi. And again, rho is held constant because you don't want the interior, so you're not letting the radius go from 0 to r. You're holding it, your rho constant at 1, so you only get the surface of the sphere. The next thing I did is I calculated my vector normal. I guess this should be a lowercase. I'm sorry, the other book I have uses different notation. So my vector normal is going to be my t partial derivative with respect to my first variable crossed the tangent vector partial derivative with respect to my second variable. So here I have t theta and t phi. So this first line here for my cross product, I have my ij, k direction vector, so I should put hats on them. And then my next line is my partial derivative with respect to theta. So over here, first I take the partial derivative of x with respect to theta, which is minus sine theta sine phi. Partial derivative of my y coordinate will be cosine theta sine phi. And then partial derivative of my last coordinate with respect to theta is 0. And then this next line here is my t with respect to phi. So that will give me cosine theta cosine phi, sine theta cosine phi, and this will give me negative sine phi. And I do the determinant calculation here, and I get this as my final answer, minus cosine theta sine squared phi. My next coordinate is minus sine theta sine squared phi, and my last coordinate is minus sine phi cosine phi. And then as we were talking about the positively oriented surface normal, then is cosine theta sine squared phi, sine theta sine squared phi, and sine phi cosine phi. The next parameterization I will do is surface of a cylinder, and much like we did for the sphere, we consider how would we parameterize an entire cylinder, including the interior, and we would use cylindrical coordinates. So we have a cosine theta, a sine theta, and z, where theta goes between 0 and 2 pi, z goes between 0 and h, and our a will go all the way from 0, the middle of the cylinder, all the way out to the edge, r. So you can see by letting a go from 0 to r, we get the entire interior part of the cylinder. And using the same reasoning as we did for the sphere, the surface of the cylinder then, we get the surface by holding the radius constant at a. In other words, we don't let it go from the center all the way out to the edge of the cylinder, or the surface of the cylinder. We hold it at its radius. So now we have phi of theta z is equal to a cosine theta, a sine theta z, where theta goes between 0 and 2 pi, and z goes between 0 and h. Again, I have my normal calculation, and I should change my notation so it looks more like this class's book. So we have t theta, derivative with respect to theta is minus a sine theta, a cosine theta, this has no thetas in it, so it's 0, and tz with respect to z is equal to 0, 0, 1. So I do my cross product, and I get my vector normal to my cylinder is a cosine theta, sine theta, 0. The last surface I will do is that of a cube, and we want to consider the cube as a union of 6 faces. So we have S1 now, I'm going to consider this yellow face, and S2 will be the green face. So S1 being the yellow face here, it kind of looks like it's pointing to this bottom on the plane, but on the XY plane, but it's not. It's this yellow, so I'm going to underline it in yellow. And that's where, and this is a, I should have said this is a unit cube. So this face is at x equals 1. This is my x-axis, and this is 1. So to parameterize this, we have our phi of yz is equal to, our x is held at 1, y and z vary, but y and z vary between 0 and 1, and that will give us all the points in this yellow square. S2, this surface here is at y equals 0, so our phi then is going to be dependent on x and z, and it's all the coordinates x, y is equal to 0, and z, where x and z vary between 0 and 1. And I went ahead and I did my calculation for the normal vector for S2, that's the green. So my partial derivative with respect to my first variable x is equal to 1, 0, 0. Partial derivative with respect to my second variable, that's z, is 0, 0, 1. I do the cross product and I get 0, negative 1, 0, which is easy to see that would be the case because on this green face, you can see the normal vector points straight to the left in the negative y direction, which is exactly what we have calculated. Now that we discussed how to parameterize surfaces, we can now look at the surface integral operator on a vector field using the dot product. So here's the notation, our surface integral operator dotted with a vector field, and I should put a line to denote this is a vector field. There are 4 steps to evaluating this integral. The first step is to parameterize our surface and determine its domain. So that's what we were doing when we did the sphere, cylinder, and the cube. We determined our mapping and we determined our domain. Then we're going to write our vector v here in terms of our parameterization, and the idea is that v is a vector field over the entire 3-dimensional space, but we're only concerned about the vector field on this surface. So we do v composed of our surface. Then we calculate our vector normal, and finally we plug in to this integration formula that we're going to integrate over the domain. That means this is a double integral, and we're using our parameterization d over here to determine our limits of integration. We plug in our v composed of phi, and then we dot that with our vector normal, which is tu cross tv. We will do this example here next. Oh, and one other thing I should mention, the physical interpretation of this surface integral is flux. That is, it's the rate of flow across the surface. And the problem is to compute the surface integral of the radial vector field, so our vector field v is given by r of xyz is equal to xyz, so it just radiates out over the surface of a unit sphere. Our first step is to parameterize our surface and determine its domain. And remember, when we parameterize the surface of a sphere, it's much like writing out spherical coordinates, except now because it's the surface of the sphere, we want to set our radius equal to the radius of the sphere. In this case, it's a unit sphere, so the radius is equal to 1. So we have cosine theta sine phi, sine theta sine phi, cosine phi. And again, the radius is set to 1 because we don't want the interior of the sphere, like we don't want the center where the radius is 0. We only want where the radius is equal to 1. And then our theta goes between 0 and 2 pi, and our phi goes between 0 and pi. These become our limits of integration. This is also our domain. It's the domain of our parameterization of our sphere. Step 2 then is to write our vector field in terms of our parameterization. In other words, compose our vector field with the parameterization. So our vector field is the radial vector field, so we want r of phi. So I just plug in phi into r. So we have r, our cosine theta sine phi, sine theta sine phi, cosine phi. And when this is r of my x, y, z, and what it returns is just x, y, z. So I get back my cosine theta sine phi, cosine phi. So r doesn't do a whole lot, right? It just takes your vector, returns the same vector. So that's exactly what I've done here. R takes this vector, returns the same vector. The next step is to calculate our normal. That's tu cross tv, where u is our first variable in our parameterization, and v is our second variable in our parameterization. So the tangent, or the partial derivative with respect to t, so I'm looking at our parameterization, our first partial derivative with respect to, our first variable, which is theta now. So partial derivative of this vector with respect to theta, we'll get the minus sine theta sine phi, a positive cosine theta sine phi, and over here we'll have 0. For our t of phi now, so partial derivative with respect to phi, we're going to have our cosine theta cosine phi, partial derivative again with respect to phi, so we have our sine theta cosine phi, and here partial derivative with respect to phi is negative sine phi. Now we take the cross product of the two and we get this normal here, which is negative cosine theta sine squared phi minus sine theta sine squared phi and minus sine phi cosine phi. And you'll notice you can factor out the negative, but what we have now is the negatively oriented normal. Remember, surfaces have a positive orientation and a negative orientation. So for our surface integral, we need to make sure we take the positive orientation. So I'm going to take this normal, and I'm going to make it positive, and now I have my normally oriented surface, my positive orientation of my surface. And now I can plug all these elements into my integral. So I have the double integral over the domain. So that's going to be 0 to 2 pi of d theta, 0 to pi d phi. And then I'm going to have my vector field composed of my parameterization. That's this over here. Cosine theta sine phi, cosine phi. That's this here. And then I'm going to dot that with my vector normal. And I'm going to use the positive orientation. Cosine theta sine squared phi, sine theta sine squared phi, sine theta cosine phi. The next thing I did over here on my vector normal, I factored out a sine phi just to make things a little easier, because you see when you dot this radial vector field with the rest of the normal, you're going to get something that simplifies or goes to 1, which means our integral is greatly simplified to the integral of sine of phi. And when you integrate, your final answer is 4 pi, which tells you that you have a positive flux and an outward flow. And I'm going to make a comment here. When I originally posted this video, I forgot to use the positive oriented normal. And William, one of the viewers, had made a comment to me, and he said, well, because I had used this wrong normal, I had a negative flux. And what William asked was, how can you have a negative flux when you have this radial vector field which radiates out? And he was absolutely correct. There was something not right. And so I realized, oh, I had forgotten to use the positive normal. And so you can see that if you forget, you'll get solutions that won't make sense when you think about it physically. So it's important to remember to use the correct normal. Our next example is to compute the surface integral f of xyz equals xy squared y over the surface of a cylinder with radius 1, x squared plus y squared equals 1, bounded by z equals 1 and z equals -1, so it has a height of 2. So I've drawn this cylinder here, and we're only concerned with the surface, so not the interior of the cylinder. And so much like the cube, I'm going to consider this a union of three surfaces. First is kind of this body, the part that rolls around. I'm going to consider that my first surface, S1. S2 is the disk that's on top here, and S3 is the disk that's on bottom. And I call it a disk because the difference between a circle and a disk is the circle is equidistant from the center, so it's just the outline. If you want the interior as well, that would be the disk. What I am going to do is compute the surface integral across surface 1 and surface 2. I will leave surface 3 for you to do. And essentially, by my physical interpretation, I'm going to calculate flux across the body of the cylinder and flux across the top of the cylinder. The first step is to parameterize the surface S1. And this is our cylinder that we had talked about earlier. So we parameterize it based on cylindrical coordinates, except that we hold the radius at 1. So we have phi of theta z is equal to 1 cosine theta, 1 sine theta z, where theta goes between 0 and 2 pi, and z, remember, goes between -1 and 1. And again, this 1 is here because the radius of our cylinder is 1. If the radius had been or if this, had been x squared plus y squared equals 4, the radius would have been 2. In front of this cosine would have been a 2, and a 2 in front of the sine instead. But our radius is 1, so I put the 1 in front. Step 2 is to write our vector in terms of our parameterization. So here's our vector f of x, y, z. I'm going to plug in then our parameterization. So for x, I'm going to plug in cosine theta. For y, I'm going to plug in sine theta. And for z, I'm going to plug in z. So f of this x, y, z is the first term, or first coordinate, is x, y squared. So that's cosine, that's my x, times y squared is sine squared x. So that's my first term. My second term is x squared times y. So x squared will give me cosine squared theta, and y gives me sine x. And finally, for my last term, I shouldn't call it term, coordinate, I'll put my y. So sine theta is in my third coordinate. The next step is to calculate the normal. So the first thing I do, I come back to my parameterization. I calculate the partial derivative with respect to the first variable, and I get minus sine theta, cosine theta, and 0. I calculate the partial derivative with respect to my second variable. I get 0, 0, 1. That's like really nice, because then when you take the normal, when you do the cross product, it's relatively easy, and the norm will be cosine theta, sine theta, and 0. Finally, I plug it into this formula here. I take the integral over the domain, and the domain is given to me here in the parameterization. It's a double integral, 0 to 2 pi, that's my d theta, which I forgot to write, and then my -1 to 1, that's my dz. Also, I forgot to write that. But now I take my function composition, which I have over here, my cosine theta, sine squared theta, my cosine squared sine theta, and my sine theta dotted with my normal, which is over here, cosine theta, sine theta, 0. After a bunch of calculation, I see that my answer will be equal to pi. This means that the flux, there's a flow outward at this rate of pi. Next, I will calculate the flux across the surface S2. In this case, S2 is two-dimensional, and it's a circle. And to parameterize it, I am going to use polar coordinates. So my phi of r theta is equal to r cosine theta, r sine theta, and my z now is held fixed at 1. And so one of the things to notice is, okay, my theta is going to go between 0 and 2 pi because I have a circle. My r now is going to go between 0 and 1 because at this point, I really do want the interior of the disk I want the radius to go from 0 all the way out, right? And I want to do it all the way around in the circle. That's how I'm going to get this entire surface colored in blue here. And again, just to belabor the point, that's different than when we parameterize the body, this roly-roundy part of the cylinder, because we only wanted the exterior. If we went from 0 to the radius, what is the radius? 1, we would have gotten the entire interior. But by holding the radius equal to 1, we only got the surface here. But now we're looking at the surface being the entire disk on top. My second step is to write my vector field in terms of my parameterization. So that's F in terms of my r cosine theta, r sine theta, and 1. So I plug these in to my xy squared. So that will give me x r cosine theta times r squared sine squared theta. So I'll have an r cubed cosine theta sine squared theta. Next, I need x squared times y. So I square r cosine theta and I multiply it times y. And I get r squared cosine squared theta sine theta. And finally, I put in y for my last coordinate. So that's r sine theta. Next, I calculate t theta cross tr. I calculate my normal. So I take the partial derivative of this with respect to r. I take it with respect to theta. I do the cross product, and my answer is 0, 0, r, which is quite nice because when I do my last step, I'm going to plug in this formula, and because of the dot product, the zeros cancels out a lot of things. But anyway, I'm doing my integral over the domain, so it's a double integral, and my domain here is given as 0 to 2 pi, that's d theta. And then on the outside, I have 0 to 1, and that's r. I do my dot product of my normal with my function composition. This goes to 0, this goes to 0, and all I'm left with is r squared sine of theta. And that will give me, for final answer, 0, which means there's no flux in the top, from the top. I have not calculated the flux at S3, but I believe that answer is also 0, but I will leave that for you to confirm. That concludes the material for this video. To review what we've discussed, first we talked about the surface integral operator, and that is this integral over a surface of d sigma. We talked about that the surface having an orientation, and for a closed surface, the positive orientation is going out of the surface. And then we also talked about when we don't have a closed surface, in other words, something that doesn't have an interior, something like this surface here, we talked about imagining traversing the surface in a direction that if we were walking along the boundary and our left arm pointed toward the center, we use that as the direction that we're walking. And then if you curved your fingers around that direction, your thumb would point up in the positive direction. The next thing we did is we looked at parameterizing a surface, and we considered a surface, the parameterization, as a mapping from some domain in R2 to a surface in R3. So our surface is equal to this mapping of this domain in R2. And we spent some time to parameterize a sphere, which was, if we wanted the surface of a sphere, it was based on spherical coordinates, but we held the radius constant. Similarly, for a cylinder, the parameterization of a surface of a cylinder was based on cylindrical coordinates, but we held the radius constant. And then finally, for the parameterization of the surface of a cube, we considered the cube the union of 6 faces, and then we parameterized each face separately. If you had to calculate the flux or this integral operator over a cube, you would break it up and do the integral over each face. So once we talked about parameterization of a surface, we talked about applying the surface integral operator then to a vector field using the dot product. And there were 4 steps we had in doing this calculation. The first one was to parameterize our surface and determine its domain. The second is we wrote our vector field here, this vector field V, which I should put a line over. Gosh. That isn't a very nice line. So let me get rid of that and put a line over it here. Then we compose our vector field with our surface parameterization. And the reason is our vector field is defined over the entire space, but we're only concerned with the vector as it pertains to the surface. So we do this function composition. We calculate our normal to our surface by taking the partial derivative of our parameterization with respect to the first variable, partial derivative with respect to the second variable, and then doing a cross product to get the vector normal. And then finally, we plug in all these components into our formula. This is a double integral because it's over the domain, and these are our limits of our double integral. We have our function composition here dotted with our normal. We did this example of computing the surface integral of the radial vector field r of xyz equals xyz over the surface of a unit sphere. And the last thing we noted is there's a physical interpretation to this surface integral on a vector field, and that is a flux. That's the rate of flow across the surface. So that's it for this video. Thank you for watching.